Hi, my name is Sebastian Matteau and today I would like to demonstrate DataMatrix. Now, DataMatrix is a Python module for numerical computing, so it's kind of in the same genre as libraries such as NumPy or Pandas, if you may be familiar with those. But DataMatrix is a bit different in that it offers a very user-friendly and very readable syntax, so that is one nice property of DataMatrix. And DataMatrix is also very useful for the kinds of analyses that I'm going to show today, in which you have a mixture of continuous and non-continuous data. Now with that I simply mean that continuous data is data of the kind that you get, for example, if you do an EEG experiment where you record brain activity over time. So the brain activity, the EEG signal, would be a continuous signal that you record for multiple time points. And then you have non-continuous data, and that would, for example, just be a button press that if the participant, for example, presses a key on the keyboard, you have a single measurement, right? A single response time or a single key that the participant pressed, etc. Now, and traditionally those kinds of continuous and non-continuous data are very difficult to mix within a single data structure, and DataMatrix makes that very easy. So now I'm going to illustrate DataMatrix using data from a psychology experiment, and it's actually an experiment that I did myself. So I'll very briefly say what we did. It's very simple. Participants simply read words, and the words could be either associated with darkness, so words such as night or shade, etc., or they could be associated with brightness, so words like sun and daylight, etc. And what we did at the same time is measure the size of the eye's pupil of the participants. And what we found was that the pupil was a little bit bigger when participants read the words associated with darkness compared to when they read the words associated with brightness. So in other words, reading about brightness or darkness had more or less the same effect as actually being in brightness or darkness, which also affects the size of the pupil, of course, but to a much lesser extent, right? So that's the data that we're working with. Now, and we're going to take this data set, experiment 1 from a paper that we published on that, and analyze it from start to finish so that you can see all the steps in processing that data. So I think this is especially useful if you do eye movement or pupil size research yourself, but also if you work with different kinds of data such as EEG data or other kinds of data in which you have to analyze time series or continuous data. This tutorial may come in very handy because lots of those different kinds of data actually have to be analyzed in a very similar way. So without further ado, let's take a look at the data. So here we are now. So as I said, we're going to analyze data from an experiment, this experiment from this paper, and we're going to analyze the data from experiment 1. Now we need a few things, you probably already have them. We need Python with the standard NumPy stack, meaning NumPy, SciPy and Matplotlib. We also need DataMatrix, which you can pip install if you don't already have it. And we need iLink parser, which you can also pip install if you don't already have it. And you can find more information about DataMatrix and iLink parser under these links. Now, so the data that we have, the data that was collected in this experiment, is data from an iLink eye tracker, an iLink 1000. And the iLink stores the data in a particular way, and we need to convert this data to a data matrix. And the data matrix is essentially a spreadsheet-like data structure. And to do this, we can simply use the iLink parser. We can say iLink parser, and then we can say dm is iLink parser.parse. Now, this will work if I run it up. You will see that it starts parsing the data. This will work because I have stored the data in a way that follows the conventions of the iLink parser. So I've placed the data files in a subfolder called data, and I've written messages in a particular way to the data file so that iLink parser knows how to handle that. Now, I will cancel this. So if you want to write your create data files that are easy to analyze, you can find the conventions to use here on the iLink parser README, right? That will really make your life a lot easier. But even though this works, it is actually not optimal because there are a few things that we're not doing here simply by calling iLink parser.parse. The first, and that is relevant to analyzing any big data set, is that we're not caching the result of our parsing, right? Parsing the data takes a long time, it's very slow, and we don't want to do this over and over again every time that we run our script. So what is better is to cache, or as it is called, memoize this function. So what we need to do, we say, okay, we define our own function, getData, and in it we say return iLink parser.parse, And instead of calling iLink_parser.parse directly, we call getData. And then what we do is we decorate getData with the Memoization decorator. So I say from DataMatrix import functional sfnc, and then here I decorate this function with fnc.memoize. What does this do? Well, it remembers the return value of getData, and then the next time that we call getData, it will return that return value right away. In other words, it avoids us from having to parse all the data over and over again. We can make it even better by saying persistent is true. If persistent is true is passed to Memoize, it means that the results of getData are written to disk, and even if we close the Python interpreter and we start our script completely from scratch, it will still work. So this is already a massive improvement. But there are a few other things that we can do. First of all, we can pass a few arguments to iLink_parser.parse. We can say, okay, first of all, we want to have a trace processor. Trace processor. Oh. What is a trace processor? Well, every time that the iLink parser encounters a trace, meaning a period of data, a period of eye movement data, and a period of pupil size data, it is passed to a trace processor function, which, for example, does some basic pre-processing. It removes blinks from the signal, right? So it reconstructs periods during which the eyes were closed. And it can do a few other things. For example, it can downsample the data, right? So downsampling means that normally the iLink records with a frequency of 1,000 measurements per second, so 1,000 hertz. And if we downsample it to say 100 hertz, it makes the data much smaller and much more easy to work with. So how do we pass a trace processor to iLink parser? Well, we can say iLink parser dot trace processor, default trace processor. So that is already creates a function for us that already implements a trace processor. So it implements basically a way to treat our traces, and we can specify blink reconstruct is true, meaning that we want every trace, the blinks in every trace, to be reconstructed whenever possible, and we also want to downsample by a factor of 10. Now, you can seems a little bit like black magic, and in a way it is, but just remember this way of specifying trace processors when analyzing iLink data, right? So what formally happens here is this is a so-called factory function that returns another function, and that function is then used as a trace processor. So it's a kind of higher level function that actually in turn generates another function that is an actual trace processor. So that's what formally happens. But basically, if you just do this, you will see that it works. Now, we also don't want to log every phase, right? So a phase is basically a period during our experiment during which something happens. And there are a few phases, but we're not interested in all phases. And if we nevertheless store all phases, it will make our data very big. So what we can say, okay, we can say pass a phase filter. And the phase filter has to be a function that says yes to all the phases that it wants to keep and says no to all the phases that it doesn't want to keep. So I'll write the lambda function, gets the name of the phase, and it simply says if the phase is target, then it returns true, right? Because this will evaluate to true if the phase name is target, and false otherwise. And this will allow us to keep only the target phase. Now, finally, we say max trace length is 300, so we limit the length of our trace to 300. We have downsampled our trace by a factor 10, meaning that we're only keeping 3 seconds of the target phase. That's essentially what we're doing here. Now, then to make life even a bit more easy for ourselves, we say dm.pupil is dm.ptrace target. So the iLink parser will create a pupil trace, ptrace, for the target phase. That's what this means. But the name is a little bit clunky, so we simply create a new column that we call pupil. That's easier for us to think about, right? So that we don't have to remember that the column is called ptrace target. And then, before we return it, we say, okay, ops.keep only. Now, what is ops? Ops is another library from DataMatrix. From DataMatrix, import operations as ops. And it allows us to keep only a few columns from our trace. from our data matrix, because you will find that the data matrix will contain many columns, and we're only interested in a few. So to keep things manageable for ourselves, we will keep only the pupil trace, the subject number trace, phase, I should say, column, I should say, type, word. So type will specify whether we are dealing with brightness related words or darkness related words. Word will contain the actual word. Subject number will contain the subject number, right? Because we have 30 subjects. Correct. So whether participants gave a correct response or not. Response, what the participants actually responded. And the response time. So a time in milliseconds that it took participants to respond. And then we return this data matrix. Now, so this is, I hope you kind of understand what's going on here. So we call iLink_parser.parse. Doing that by itself would already have been enough, but here we are a little bit more fancy because we specify a trace processor that does automatically blink reconstruction for us and downsamples the signals by a factor 10. We have a phase filter that only accepts the target phase, which we're interested in, and we have specified a maximum trace length of 300 for essentially the target phase. Then we have renamed our ptrace target column to pupil because that's a better name, I think it's easier. And then we have removed all but a few columns and we return the data matrix. Now, let me run this up. Now it gets to work, but this will take a considerable time. All right, it will take 10 minutes or so because it's a big data set. So I'm going to get a cup of coffee and I will get back when this is done. And you as a viewer just keep watching these dots move until the data has been completely parsed. Okay, we're back. The iLink parser has parsed all the data, generated a lot of output. Just to show you that now if we run it again, I will run it again and you will see that the function returns right away. Right? So we have memoized our data file and now we can rerun this as many times as we want without having to wait another 10 minutes. Now, so let's move on to actually processing the data. So what does our data look like? I will just print it out, print our data matrix, so that you have some idea of what our data structure looks like. And what you see is we have a few, right? We have essentially a table. So every row is one trial, so one word that the participant reads. So here are the words. These are the response times, the subject number, what participants responded, whether it was correct, etc. Now we have, so these are very simple. All the columns that we see here are very simple. They have a single value. But if I print out the pupil column, you will see that it's a little bit different. So the pupil column is actually two-dimensional. So we have our rows here, and then we have our pupil size over time during an individual trial, right? So it's kind of like our pupil sizes stick out of our table. Right? So if pupil size would be here, it would not be a single value, but it would be a whole bunch of values. Now, what do we want to do first in analyzing this data? First of all, we want to remove trials in which the response was incorrect. So here we have our correct column, and what I'll just say is dm.correct is 1. So this is data matrix syntax for making a selection and selecting only those trials on which dm correct was 1. So I'll print before, I'll say, okay, print n trials is length data matrix, and also after I'll do it again to see how many trials we discarded. Then we want to select only the trials on which the word type was either dark or light, because those are the trials that we're interested in. We also have filler trials, control trials. We have trials on which there was an animal word presented to which the participant had respond. We have NA trials, which were practice trials, but those are not interesting. We only want to have the light and the dark trials. So what I will do is dm.type is light between parentheses, or again between parentheses, dm.type is dark, right? And this is data matrix syntax for selecting based on one or two criteria. So we select either the light or the dark trials. Now, if I run this, what will happen? We have first 3,990 trials, and after the selection, we end up with 2,000 something. Now, that's pretty nice. Now, let's move on to baseline correction. What is baseline correction? Well, baseline correction is a technique to sort of normalize our pupil sizes. So on every trial that the participant reads a word, the pupil has a particular size to begin with, and that sort of baseline pupil size fluctuates over time, and it's kind of a source of noise. So what we do is we subtract the baseline pupil size from the signal so that all pupil size traces start at 0, right? We sort of compare pupil size relative to our baseline period. That's a very standard technique in pupillometry, EEG, etc. Now, before we do that, we actually want to make sure that we can do it safely, because there can be a problem, namely if some baseline values are very low and we baseline correct a trial based on this very low baseline value, very small baseline value, we get enormous pupil sizes, and that can distort our data. So what we need to do first is just take a look at what our baseline pupil sizes look like to get some idea of our, what kind of data we're dealing with. I think it's always a good idea to visually inspect your data. So what do we need? Well, we need matplotlib, right? The standard plotting library. Import pyplot as PLT. We also need from DataMatrix import series as SRS. So the series library, the series module, has a lot of functions for working with series data. In our case, series data is the pupil size data, right? Those are series, time series. And what we do, first we say pupil baseline. So we create a new column that has the baseline pupil sizes. Now, what are the baseline pupil sizes? First of all, we say series.window, dm.pupil 0,10. In other words, we take the first 10 samples from our window, from our pupil size trace, and we create a new trace with that, with the window function, right? So that's a window on the first 10 samples. But that's not enough. What we want to do is then reduce this, srs.reduce, this window. And what reduce does, it just takes the mean. In other words, our baseline is now the mean pupil size of the first 10 samples. And that's pretty fine. What we can then do is we plot plt.hist. We say, okay, dm.pupil baseline. We want to have 100 bins. And we want to plot it within a range of, say, 0 to 5,000, because I know that according to the iLink, pupil size values tend to range sort of in this general range. And then I want to show it. So let's run this up. We get a few warnings. These warnings arise because some trials don't have any data in them at all. So if we then try to reduce them, we get a warning, but that's fine. Those trials will be ignored anyway. But what we see here in our histogram is that pupil size, baseline pupil sizes are, well, I wouldn't say they're normally distributed, but they have kind of a right tilt distribution. And I would say based on this that any baseline pupil size larger than 400 and smaller than 4,000 is more or less realistic. So let's remove all those trials on which baseline pupil size is unrealistically large, simply just because those can distort our data. Now, you will note that I do this very much by eye, and I think that may not sound very scientific, but I think at the moment it's the best we can do, right? So visually inspect your baseline pupil sizes, and based on this visual inspection, just make a sensible, justifiable decision on what you think realistic baseline pupil sizes are. So before trimming, again, I will print out the number of trials, because then we can see how many trials we've lost. And what I say is pupil baseline is larger than 400. So those are the trials that we want to have. And the trials where the pupil baseline is smaller than 4,000, right? So it has to be both larger than 400 and smaller than 4,000. Now, and then print after trimming, just so that we know that we don't lose an excessive amount of data or that we do something wrong, right? Because we should not lose a lot of data here. We discard only a few trials. So let's run this before trimming 2034, after trimming 2019, right? So we have actually a very clean data set. That's pretty nice. And again, we get some warnings, but that's fine. Those warnings are not that important. Okay, now the baseline correction. I accidentally left the code still here. So how does the baseline correction work? Well, we have the baseline function from SRS, right? The series module of DataMatrix. We specify one column that we are going to apply the baseline to. We specify another column that we're going to use as the baseline. In this case, those are the same columns because we're going to use the beginning of the pupil trace also as the baseline of the pupil trace. and we're going to use the first 10 samples. And then the baseline corrected pupil trace we're going to save as dm.pupil_blc, right? Let's run this up and we're done. So that was the baseline correction. Okay, now we need to now we're going to actually do something interesting with our data. We have done the pre-processing essentially. So now we're going to plot it. So what are we going to plot? Well, we're going to plot pupil size over time separately for trials on which participants looked at brightness conveying or darkness conveying words. So what we're going to do, first of all, we're going to split our data set. dm light and dm dark is ops. Now dot split. Oh. Now what is ops.split? Ops.ops is from DataMatrix import operations as ops. So ops is the operations module from DataMatrix, and this has a split function, and the split function allows us to specify a column, and then we can say, okay, light and dark, and what it will do, it will split the data matrix based on this column and these values, and then return that as a tuple that we can assign here with multiple assignment, right? So we get one data matrix with the light trials and one data matrix with the dark trials. Now, and then very simply we can say, okay, plt, right, plot from matplotlib, plt.plot dmlight.pupil. We cannot plot pupil right away because we have a lot of individual trials. What we want to plot is the mean pupil trace, dmlight.pupil.mean. What kind of color? Color is orange. I think orange is a nice light color. Label is just so that we know, okay, light and the number of trials that are in there. Length dm light. Yep. And we want to do almost the same thing for dm dark, right? Dark, blue, and dm dark. And then I will say plt.show. Now let's run it up. Okay, now here you see the results. If you know the paper, you will see that this resembles the results from the paper very closely. I also see that actually here on the y-axis, I note that those are the original pupil size values. And that's because I'm plotting the original pupil size and not the baseline corrected pupil size. So I wanted to plot the baseline corrected pupil size. Up, there we go. Now we start at 0. But you see it doesn't make a big difference, right? And that's healthy because if it makes a big difference whether you plot the baseline corrected pupil size or not, that means that there's something funky about the data. But in this case, there's not. So what you see here is that indeed the blue trials, so the ones that that correspond to the dark words, are a little bit larger than the ones that correspond to the bright words, right? That's the crucial finding. Now, what this plot is definitely missing is error bars, because we want to have some kind of measure of variation. So what we want to do, okay, we want to define a function. I will call it plot series. And it will take a series. It will take a color and a label. And what it will do, first of all, it will create a range for the x-axis. Series.depth. A series has a depth, right? So those are how many time samples there are. In this case, the depth will be 300. That's the depth of our pupil series. You know what? Let me rename this to pupil to avoid confusing this with the series module, which we've imported before, right? So that's not very nice to use the same name for two different things. Okay, the y value is our pupil.mean. And we have a standard deviation, which is the pupil.std, so the standard deviation of our pupil size, divided by the sqrt of the length of pupil. Now, what is NP? It is NumPy. Import NumPy as NP. In other words, this is our standard error, right? The standard deviation divided by the square root of the number of observations gives you the standard error. What is the standard error? Well, it is a measure of the precision of your data. So how accurately you know whether you're measuring the true signal, essentially. Then what we do is we say plot fill between. That's going to draw our error shadings. I say x is x, right? The x coordinate. The y1, so the upper band, is y minus the standard error. y2 is y plus the standard error. The color is the color that we passed. and then we're going to say alpha is 0.25. Alpha is a transparency, and we want to have our error shading sort of semi-transparent because that just looks nicer. And then we're going to plot plt.plot y, color is color, label is label, and that's going to be the line that is actually inside our error shadings. Okay, you will see what this looks like. And then instead of here plot.plot, we say simply plot series dm light pupil BLC, and here we say plot series dm dark pupil BLC. We specify the color and the label, and what I forgot, we also say plot a legend so that we can see it. Now, okay, let's run this up, and now you see we have the same figure, but it's nicer because we have a legend, which I forgot before, but especially also because we have our error shadings, right? So you have some idea of the variability in the data, and you see that it's, I wouldn't say that it's a very big effect, but it's a pretty robust difference between the two lines. Okay, now, so these are the overall results. You know what I'm also going to do, just to make it look nice, I'm going to say plt.ax hline 0, color is black, so I'm going to up, and line style is up. If I run this, just to get a nice up 0 baseline, right? So you see we started our baseline value of 0 because we baseline corrected the data. Now, this is pretty nice, but this is average data, and I think it's always healthy to look at individual participants. Why? Well, just because you want to have some idea of whether all participants show the effect or not, right? Is it the case that this line is above the other line for all of our 30 participants? That's very unlikely, right? Because participants differ quite a lot. But how is this? What does our variability look like? So let's look at data from individual participants. So the first thing that we're going to do is plot a trace for each participant, and the trace is going to be the difference between these two lines, right? So then we have one line for every participant that reflects their effect size, essentially. So what I'm going to do first, for subject number, comma, dm subject, in ops.split dm.subject number. So here I'm using the split function again. Now, if I just call split function with only a column and not specifying any values afterwards, what it will do is it will split the data based on all values, so all subject numbers in this case, and return an iterable where of tuples where the first element is the value that is split, so subject number in this case, and the second is a data matrix with the subset of the data. Right? So it's pretty intuitive, I think. And then we're going to assume that we have a function which is called plot subject. Plot subject trace, let's call it plot subject trace, and we pass dm subject to it. Then we're going to again get our horizontal line. You know what, I'll copy that from here. Up. And plt.show. Okay, so what we still need to do now is define our function plot subject trace that takes a data matrix. How are we going to do that? Well, we're again going to say dm light, dm dark is ops.split dm.type light, comma, dark. Right, so we split our data into the light and the dark data trials. Now, what is our y value that we want to plot? Well, it is the dm dark baseline corrected pupil size, the mean of it, minus dm light, the baseline corrected pupil size, also the mean of it. Right? So we take the mean pupil trace over time for the light trials, and we subtract that from the mean pupil trace over time for the dark trials, and that's going to be our line for this particular participant. And then we say plt.plot y, we say color is green, because I think it's a nice color for a participant, and we say alpha is 0.25 because we're going to have 30 lines, so if they're a little bit transparent, it will make it easier to see. Okay. Now I think this is correct. Let's run it. Up. Okay, there we have it. So those are the individual participants. So lines that are above 0 show an effect in the overall direction. So right, so dark words give a larger pupil than small words, and trials that are below give an effect in the opposite direction. And you see that the majority of the participants have effects in the predicted direction, but there is especially one participant, this one, that has a pretty big effect in the opposite direction, right? And to my eyes, this participant actually looks kind of funky, this kind of very jagged pattern of results suggests to me that maybe the data recording didn't go optimally or anything like that, right? But still, we're going to leave that participant in because we don't really have any very clear reason to exclude him or her either, right? So I don't really, not particularly happy with that, but I think it's the neat thing to do. Now, so looking at this graph, it's very difficult to interpret, right? It's a bit of a mess. Let's take a look at the participants in a more structured way by taking each participant, getting the effect size for each participant as a single value. And what is the effect size for each participant? It is basically the surface below each line, right? So participants who have an effect in the opposite or in the predicted direction would have a positive surface, and participants such as this participant here would have a negative surface, right? And then we take that surface between the line and the zero line as a measure of their effect size. Now, how can we do that? First of all, we're going to define a function which I call effect, and the effect takes a data matrix, and what it's going to do is return a single value that calculates this surface, right? That's an effect size for a particular participant. So again, we're going to split our data. dm light, dm dark is ops.split, dm split, dm.type light, comma, dark. Now, then we get the mean pupil trace for dark trials. So dm dark, SRS does reduce, dm dark dot pupil blc dot mean. So what this does is it takes all the baseline corrected pupil traces for that participant. It reduces those so that instead of a series of instead of multiple traces, we have multiple values for every trial, and then we get the mean value, right? So that's kind of the mean effect size across trials for that participant. And for the bright trials, we do the same thing. So basically, we're working with data that's aggregated at different levels, right? On different levels. So that's a bit difficult to wrap your head around, but basically, I will go over it again. We take, for the dark trials, all pupil traces, the baseline corrected pupil traces, and we reduce them so that we end up with a column of mean values, mean pupil sizes. And then we take the mean of that column, and we end up with the mean pupil size overall for the dark trials. And we do the same thing for the light trials. And what is our effect then? Well, the effect is simply dark, return dark minus light, right? So that's the effect size of a single participant. Now, how are we going to use that? What we're going to say is EM is data matrix. What is data matrix? Well, it's obviously a data matrix object, but we haven't actually imported that yet. So I still have to say, okay, from data matrix, import data matrix, right? So data matrix with capital letters is the data matrix class, and we create an instance of a data matrix like this. How long is the data matrix? Well, it's as long as there are subjects. So the original data matrix has subject number, and it has count number of individual unique values. Okay, then we say em.effect, so we create a new column, and here we're going to use a bit of Python magic. What we're going to say is a list expression, and we're going to say for subject number, comma, dm subject, in ops.split, dm.subject number. This may look familiar, right? So we have a for loop that's based on a split of the data by subject number. But instead of doing this in a block of 4 statements, what we do is we have a list comprehension, and we say effect dm subject. So this is called a list comprehension, and what it will do is it will automatically traverse through this for loop and then make a list out of the effect function applied to our dm subject objects, right? Do you see the logic here? It's a list comprehension. I also have a video on list comprehensions actually on YouTube, so if you're not familiar with it, feel free to look that up. Then what we want to do is effect is ops.sort effect, em.effect, so we sort our effect column. Why? Well, because it's kind of convenient to plot the effect sizes when they're sorted, because that makes it easier to see whether overall effects are positive or not. Now, and then we're going to plot them. So we would say plot em.effect. We're going to plot them as dots with lines connected. and then a line again, h line, 0, color is black, line style is up, and we plot it, plt.show. Okay, let's run it. Okay, so what do we see here? So we have 30 participants, right? And you see that the majority of participants, these ones, have a positive effect, so an effect in the predicted direction, and a minority of the participants have an effect in the opposite direction. And you see there's one participant in particular which has a very strong opposite effect, this one, and that is this participant, right? So the participant that has this very erratic pattern. Now, so if you're not familiar with psychology data, this is actually a pretty big effect. It is almost never happens that all participants in these kinds of experiments show an effect in the predicted direction. But what we need to do is perform statistics to see if this pattern of results is statistically different from chance, right? So the question that we want to ask is if there is really no difference between the brightness and the darkness related words, or the pupil size while reading those, how likely is it that we would find an effect that we see here, or or a more extreme effect? And that kind of dense formulation is called the p-value. So I'm not going to explain p-values in detail here, but let's just say that any p-value below 0.05 is traditionally taken by psychologists to reflect an effect that is quite unlikely to have arisen from chance. Now what we're going to do is say from SciPy import stats. So SciPy is a module that has a lot of more high-level data numerical functions in it, among other things, stats. And we're going to say print stats dot t-test onesamp. Now what is that? That is a t-test that is a particular kind of statistical test that tests whether our data points that we have here are statistically different from 0. So we pass our effect. We have to say what our test value is. It is the population mean argument, pop mean, and it's 0. So if I print this up, you will see that we get a test statistics of 2.5, a t-value, and the p-value is 0.016, which is smaller, considerably smaller than 0.05. So this is statistically significantly different from 0. Now you might wonder whether a normal t-test is appropriate here, because the data may not be normally distributed. If that doesn't mean anything to you, don't worry about it. But we can do also different kinds of tests. We can say stats.wilcoxon, which is another test to test whether the effect is statistically different from 0. Okay, if we do that, we also see a p-value that's even a little bit smaller, 0.007, also suggesting that the pattern that we have observed here is statistically different from 0 and quite unlikely to have arisen by chance. Okay, now with that, I would like to thank you for watching this video. I hope you've learned a little bit about data processing in DataMatrix, but also about processing eye movement data in general, and even about processing any kind of time series data more generally. And thank you for your attention.